Hello students, in my next video on the flat slabs, we will design a flat slab. The question given for the design of flat slab is, a flat slab floor system consists of 5 panels. It is consist of 5 panels. The floor system consists of 5 panels in each direction. It is subjected to a live load of 4 kilonewton per meter square and a floor finish load of 1.25 kilonewton per meter square. Height of the column is 3 meters and diameter of the circular column is 550 mm. Support is circular, that is column is circular. We have to convert that circular column area into equivalent square area as I have discussed in my first video. Interior panel is of size 7.5 meter by 6 meters. Size of the interior panels. So obviously using IS 456-2000 provisions, design the interior panel. Okay, the problem is limited to the design of interior panel, providing appropriate column head as well as drop. The grade of concrete to be adopted is M20 and the grade of steel is Fe415. So let us start the designing of an interior panel of a flat slab system. It is clearly given that it is an interior panel. So what all provisions are given for the flat slab interior panel design in IS 456, we'll make use of that and we'll start the solution. Fine. So the first step is the given data. Just we will write out what all the data is given. In the first step, we'll write that as given data. So first and foremost thing given is number of panels. Number of panels. The given floor system, number of panels in each direction is 5. So whatever is given in the question, the same thing I am taking under step 1 as the given data, 5. Live load is given as 4 kilonewton per meter square. Floor finish load is given as 1.25 kilonewton per meter square. Height of column is given as, so all the given data of the question is being copied here. It's being taken here, 3 meters. Also because it's a circular column, so diameter of circular column is there. If it's rectangular column, then both area will be given to us. Okay, diameter of circular column or size of the rectangular column will be given to us, 550 mm. So as soon as you come to know that this is a circular column, then you have to convert the circular column area to equivalent square area. Okay, if the given column is itself a square or a rectangular, then not required. So first we will find out what is the equivalent area. Equivalent size of square column. Okay, so suppose the square column is of side S. Okay, then the equal area of a square column will be S and the area of circular column will be pi d square by 4. Okay, so S square is equal to pi into d is given as, okay, if you want to calculate it, you can calculate it 550 whole square by 4. Fine. So from this we get the equivalent side of a column. So equivalent size will be 500 mm. So as you know yesterday, as you know in my flat slab part 1 video, I have said that the diameter has to be converted into the equivalent side of a square column. So once we do it, so immediately we'll find out the size of drop, because in the question it is given that you have to select, you have to provide drop as well as head. So size of the drop is in clause 31.2.2. In my last video I have discussed all these things. So if you want to refer, it is there, IS 456 31.2.2. 31.2.2. The drop when provided shall be rectangular in plan and have have a length in each direction not less than one third of the panel length in that direction. So following that clause, that is 31.2.2, the size of the drop shall not be less than one third the panel length in each direction. Panel length in each direction. So in the question, the size of panel is given as 7.5 meters by 6 meters. So the drop size should be, okay, the drop size will be one third of 7.5 by one third of 6 by 3, one third of this. So the size of the drop shall not be less than 2.5 meter by 2 meter. So this we have to be keep keep in mind when you are fixing up the size of drop. The size of drop shall not be less than one third of panel length in each direction. So it's one third means in one direction the span length is 7.5, in the other direction it is 6. So one third of this by one third of this. So when you are designing your flat slab interior panel, you should see that this is drop size is not less than 2.5 by 2 meters. Then also it is given in the question to design to provide column head also. So let us see what should be the diameter of the column head at the top. You know what is column head? At the top of the column, the area is flared up. The size of the column is flared up, increased. Okay, so that is called as column head. So how to increase? How much should be increased? Again, IS 456 31.2.3. 31.2.3. This clause is saying that the diameter of column head at top of the interior column, at top of the interior column shall be something in between 1/4 to 1 by 5 of average spans. So it can be like this, 1/4 to 1/5 of the average span. So one span is 7.5 plus one span is 6. So this comes out to be 1.69 meters to 1.35 meters. So there is an upper bound and lower bound. You can select the diameter, the diameter anything between 1.69 and 1.35, because we have to follow the recommendations of IS 456. So let us adopt, because this is lower and this is upper bound. So let us say we will provide column head of diameter. As I said, you have the flexibility of picking up anything between these two. So to solve this problem, I have taken 1.5 meters at the top. So at the bottom it is 550 mm. The normal diameter of the column is 550 mm. That is 0.55 meters. That is being flared up to 1.5 meter at the top. I hope you are getting my point. Fine. So at the top of column. So you can see bottom it is 550 mm. It is being flared up like this. So the topmost will be 1500 mm. As I said, 1.5 meter, so it will be 1500 mm. So this angle should be 45 degree. When you are flaring it up, or when you are spreading it up, the angle should be 80 degree with an angle of 45 degree with an angle of 45 degree. So fixing up of the dimensions of column head is also completed. So we can just show it in a figure like this. I can just show figure like this. So this is the top of slab. Fine. So after some time, this thickness is suppose whatever we get according to the design, we will see it. Then there is a drop. There is a drop. Then this is the drop. Then you'll have a column like this. Column head. This is a column. Same way here. This is a column. Column is being flared up. Then this is panel. Then you'll have thickness reduced to the slab. Again after some part, again the same thing continues like this. Again you'll have a drop, okay, a drop, and then column head, then this drop will continue according to the size. Just now we have fixed up the size also, okay, according to the size we will do this, then it will continue like this. Fine. So this is how the column has been flared up to 1.5 meter. That is the diameter of the column at the top is 1.5 meter. So immediately you also have to find out the equivalent, because whenever it is a circular one, we have to convert it into equivalent side of a square column. Equivalent side of square column head. The same formula as you have seen, a square is equal to pi into 1.5, or you want to write it 1500, you can write it 1500, because if you convert that into mm, it will be 1500 mm. So this is the diameter area of the circular column. This is the area of the square column. So when you solve it, you will get the equivalent side of a square column, that is 1.34. So this is how you have converted the bottom equivalent circular was 500 mm. Now top equivalent side is 1.34 meters. 1.34 meters. So along with this, we will also fix up this clear spans. Okay, this clear spans. As I said you, the clear span is the distance between successive two face-to-face columns. So this is your clear span in one direction. Same way in the other direction. So suppose I have taken this as 7.5 meter span, then 7.5 minus this equivalent side 1.34. So this is a clear span, which we represent it as ln. This is along 7.5 meter span. So this will come around 6.16 meter. 6.16 meters. Okay, along 7.5 meter span, the clear span is, the definition has been explained in part 1 slab. What is the definition of clear span? I have already discussed it in my previous video. So I'm just calculating it, the clear span along the longer span. In the same way, you can also find out the clear span in the other directions. So that will be 6 minus 1.34. 6 minus 1.34. So 4.66 meters. Okay, suppose your L1 is 7.5 meter, then LN1 is 6.16 meter, and your L2 is 6 meters, then the clear span in that particular direction is LN2 is 4.66 meters. Okay, so this is how we have calculated the clear spans. We have provided the column heads. So let us write that in the statement wise. I have just shown you the with this near the drawing. Now let us do the same thing. Let us do the same thing here. Clear span ln1 is equal to what I did it just now. I'm just repeating it again. There I have shown it near the figure how it is exactly. So this is 6.16 meter. Okay. Now again, if you see the clause given, clear spans clause in IS 456, okay, you can see it shall not be more than 0.65 of the span in the other direction. In the other direction. Fine. In my first video, I have shown that it shall not be more than 0.65 the span in the other direction. Shall not be more than 0.65. If this is, suppose I am taking this as 1, then the other will be clear span. So that is 0.65 into 7.5. So the clear span shall not be more than um, the given span, 0.65 times of the given span. The same way in the second direction, that is transverse direction, 6 minus 1.34, that is 4.66 meters. Again, as per IS 456, this shall not be more than 0.65 of L2. 0.65 of L2 means 6. That's coming as 3.9 meters. So both are accepting the recommendations of IS 456. So this is one clear span, this is the other clear span. Fine. So this is how we have completed the dimensioning part. Now in the next step, let me say this is my step 2. So in the step 1, we have taken all the given data, and in step 2, all the given data I have taken, I have converted this. Then in step 2, we have calculated the IS 456 recommendations. We have followed, and we have found the size of drop as well as the size of column head. That was our step 2. Then in step 3, we will find out the effective depth from stiffness consideration. Okay, we have fixed up everything. Step 1 was the given data. Step 2 is fixing up all the lengths, thicknesses, diameters, or as per IS 456 provisions. Now in step 3, we will find out the effective depth. Effective depth from stiffness consideration. From stiffness consideration. So as per my last video, first we have to fix up the diamond and the thickness of the slab based on the stiffness consideration. That was clause 23.2. It was clause 23.2, that is giving us the span by effective depth ratio. That is, yeah, clause 23.2. So larger span, effective depth shall be equal to larger span. Okay, otherwise I'll just show you span by depth is equal to, our slab is a continuous slab. It has got interior panels and exterior panels. You can see in this figure, if I draw 5 panels, 1, 2, 3, 4, 5. So in this direction also 5 panels, 2, 3, 4. Let me say this one 5. So we are designing the interior panel. There are so many interior panels. For instance, suppose I have taken this one. Okay. This is also an interior panel. So it has got continuous slab here. It is continuous here. It's continuous here. It's continuous here. So we have to take the continuous ratio. That is span by effective depth is equal to 26. Because our slab is, our interior panel is continuous. It is continuous on all the four edges. Okay, so this span we have to consider shall be the bigger span. So it's 6.16 meter clear span. Fine, divided by 26, because it is slab is generally thickness is in mm. So I'm converting this meter into mm. So that will be your effective depth from stiffness consideration. That is from deflection point of view. So we got it as 242 mm. 240 mm. 240 mm. This is the effective depth of the slab or the thickness of the slab. Now to this we have to add the cover. We have to add cover. So provide an effective cover for slab. It can be like 25 mm you can go for. Okay, cover of 25 mm. Then overall depth of overall depth of flat slab D is equal to 240 plus 25. So this becomes 265 mm. So this is the thickness of flat slab. To this we have to also add the thickness of drop. That is the thickness of slab near the support. So we need it. But right now from stiffness consideration, the depth of or the thickness of the slab is overall thickness is 265 in mm. Now to this we have to add the thickness of drop also, because this is 265. Then some part will come, that is drop. So this is your 265. Okay. Now we are calculating this thickness of drop. First we'll find out thickness of drop. To that if we add this thickness, it becomes the total thickness of the drop. Thickness of drop, once again, as per the IS 456 clause, it is 1/4 the total thickness. 1/4 the total thickness. You can check it. It's there in the IS 456. So 1/4 of 265 mm. So that's coming as 70 mm approximately. 4 6 are 24, 4 7 are 28. It will be something like 65 plus something. So you have to just equate nearing it to something more than that you can go for. In the design you can go for something higher to round off the decimal points, not the lower point. So finally we get the total thickness including the drop. Thickness including the drop, or I can say thickness of flat slab near the support, because near the support you will get drop. So total was 265 plus 70. So total thickness including the drop is 335 mm, as I was showing you in the figure. 335 mm. So in the figure I was showing you, this is 335 mm. This was 70 mm. I have added this, it has become 335 mm. So with this, we have completed the concrete design. That is, thickness has been achieved. We'll go for the next step. That's our step 4. Step 4. Okay. Now, what is step 4? Calculations of loads on the, because okay, calculations of loads. Based on the loads, we get the bending moment. Based on the bending moment, we get the thickness. This thickness is based on stiffness consideration from the deflection point of view. The minimum thickness shall be 265 mm if the slab is not supposed to deflect. Okay. Now step four will be the calculation of loads on the slab. Calculations of loads. So the first and foremost load is self weight of slab. Self weight of slab. So as we all know, the load will be acting on an area. So we have to multiply the density with thickness. So which thickness? One is the thickness of flat slab away from the drop. The other one is thickness of the slab near the drop. So because when we compare the percentage of area of excluding the drops is more than the area of drops. So better we have to use the thickness of the slab. So it's 265 mm multiplied by 25 kilonewton per cubic meter, which is the unit weight of RCC. Okay, so that will come to be 6.625 kilonewton per meter square over an area. Then secondly, given loads. So floor finish load is given to you. Floor finish load that is given as 1.25. Floor finish load is a dead load. Self weight of the slab is a dead load. So first I am finding out the dead loads. Okay, these two are the dead loads. Okay, so we get the total dead load. Because there is a provision in the IS 456 that the design live load, the design total live load shall not be more than the clause is there. So we will use that clause. Design live load must be less than 3 times the design dead load. So we are calculating separately the dead load, separately the live load. So this, when I add up, this will come to be 7.8 to 7.875 kilonewton per meter square. Now, since this is a limit state method of design, we have to factor the load. We have to factor the load. So, factored dead load will be 1.5 is the factor of safety as per a limit state method. So, this comes out to be factored dead load is 11.82 kilonewton per meter square. Fine. Now, same way, we will calculate the factored live load. So, live load is given in the question. Factored live load. It is 1.5 and 4 is the live load. So, this is coming out to be 6 kilonewton per meter square. Factored live load is 6 kilonewton per meter square. Okay. Now comes the design load, that is W. So ultimately we have to add it. This is just to check the IS 456 clause, that is design live load must be less than 3 times the design dead load. To have a check on that, I have first calculated separately. Now I am adding it up. Ultimately we have to add it and find the bending moment. So design load will be represented by W. So that is 11.82 plus 6. So that has come to be 17.82 kilonewton per meter square. So this is the step 4 where we have found all the loads acting on the slab. Now let us moving further to our next step, that is step 5. Now the design part is coming. Design, we have to do the design. In the step 5 we have to do the design, but which method you are going to use? So as I said you, we will be using direct design methods. So before applying the direct design method, we should check whether it is this slab is passing through the requirement of the direct design method or not, because there are certain limitations when we are using the direct design method as per IS 456 clause 31.4.1. So let us first check whether we can use the direct design method or not. Check for application of direct design. So in short, I can say DDM, direct design method. So this you can find in 31.4.1 IS 456. These are the limitations. There shall be minimum of 3 continuous spans in each directions. So how many we have in this problem? We have 5. Minimum shall be 3. That means the first check we are passing. The first check is there should be minimum there should be minimum of 3 spans. There should be minimum of 3 spans in each direction. In each direction, minimum 3. But now, right now, we have 5 panels. We have 5 panels. So this we have passed. This limitation we have crossed. Okay. Now what is the second? L by B shall be less than 2. It is longer clear span by shorter clear span 4.66. It's coming to be 1.32. So obviously it is less than 2. So okay, we have crossed the second limitation also. Third is the one which I was discussing. Design live load. Okay, must be less than 3 times the design dead load. So design live load is 6 and 3 times of design live load is 11.82. Design dead load is 11.3. So obviously live load is less. Okay. So all these 3 limitations we have passed. So that means we can use the direct design method. So use direct design method. Direct design method is can be applied to solve the given interior panel of a flat slab system. So that step is over. So our next step will be step 6. So step 6 is determination of bending moments. Step 6 will be finding out bending moment. Determination of bending moments. So as you know, we have positive bending moment, we have negative bending moment. Okay. So and then we have to distribute that whatever positive bending moment, total bending moment you get, that has to be distributed into 2 parts, that is positive and negative as per IS 456. Then again that bending moment, whether it is negative or whether it is positive, has to be distributed to the column strip and middle strip. So before actually finding the moments, first we will find the column strip width and middle strip width in both the directions. So if that is ready, then we can just calculate, we can finish off. So if this is my 7.5 meters and if this is my 6 meters, for example, for the interior panel which I have taken, okay, so this is my 7.5 meters and this is the 6 meters. So I'll try to draw the width of, see, remember there is an adjacent span here, there is another span here, we are not bothered about it. Okay, right now we are designing only this interior panel. This interior panel. We are designing this interior panel whose width is, one dimension is 7.5, the other dimension is 6 meters. Fine. So we are going to design this interior panel. So let us draw the column width as well as column strip as well as the middle strip. So if this is 6 meters, then I am drawing the strip along the 7.5 meters. So what was given? 0.25 L2. So when I am drawing this way, so my L1 and L2 will be 6 meters. L2 will be 6 meters, L1 will be 7.5 meters. So this is the width of strip, column strip. So as we have seen it yesterday, it was 0.5 L2. Here L2 is this one because you are finding it along 7.5 meters. So this becomes L2 is 6. So 0.5 into 6 means 3 meters. So this width of strip is 3 meters. In the same way, I'll get another width of strip. Okay. So this is like there is a slab here also. So this is another column strip. Okay. Again, this is also 3 meters. So this is 3 meters. This is 3 meters. You can have a look. Out of this 3 meters, 1.5 that side, 1.5. So this is 1.5. This is 1.5. So what will be the width of middle strip? Middle strip width will be 3 meters. So in this, along the 7.5 meter, the width of middle strip as well as the width of column strip is same, 3 meters. Middle strip as well as the column strip, both are 3 meters wide. So this is how we have found along 7.5 meters length. So let us do that part here. On the drawing I have shown you. Let us do it. So width of strip. Now for this also the clause is there 31.1.1. The first clause of the first subpart of 31 clause. So width of strip. So we have to do it as per 31.1.1. So as I said you, we have got two spans. One is along 7.5 meters, the other is along 6 meters. So first we will find out along 7.5 meters. Along 7.5 meters. Okay. So L1 will be equal to, already I have drawn it. L1 will be for this 7.5 meter and then L2 will be 6 meters. Right. So width of column strip, you have to refer IS 456 clause 31.1.1. So width of column strip is given as 0.25 L2 on either side of the center line of the column. Okay. So that is 0.25 on this side, 0.25 this side. So together it will be 0.5. 0.5 L2. So that becomes 0.5 L2 means 3 meters. So let us highlight this. Then same way, and condition is also there. It shall not be more than 0.5 times L1. So 0.5 times L1 means 7.5. So that will be coming 3.75. So it's okay. The width of column strip is okay. You can go for a width of column strip of 3 meters because you are satisfying the recommendation of IS 456. So once you calculate the width of column strip, so if you subtract the remaining length, you will get the column middle strip width. So finally, I am writing as a provide 3 meters wide column strip and 3 meters wide So the remaining will be the middle strip as shown in figure. So this is how we have fixed up the width of column strip and the middle strip, only that is in case of 7.5 meters span. Okay, so similarly we will do it for 6 meters span. Now when you are doing it along 6 meters span, your L1 becomes 6 meters and the transverse span L2 becomes 7.5 meters. So taking this into consideration, we'll find out width of column strip following IS 456 provision or recommendation. What it say? It say that the width of column strip shall be equal to 0.5 L2 but not more than 0.5 L1. Now in this case, L1 is L1 is 7.5 meter and L2 is 6 meters. So this becomes 3 meters. So this shall not be more than 0.5 times of L1. Okay, this is L2 is 7.5. L2 is 7.5. So this is coming to be 3.75 meters. And zero point 0.5 times of 6 becomes 3 meters. Now you can see this is more, the width of strip is more than the limited value. So in that case, we have to limit the width of column strip as 3 meters only. You cannot go for 3.75 meters. So finally, you can write adopt column width. Okay, adopt column strip width. Column strip width 3 meters. So when column width strip is 3 meters, so the length was 7.5 meters. 7.5 meters it was. Length was 7.5 meters. Then if you want, I'll show it to you here. So like suppose this is my 7.5 meters and this is my 6 meters. Now my column strips are along the 6 meters like this. So this was my strip, column strip, whose width I got it as 3.75, but because it is exceeding, so this became 3 now. Same way here also 3 meters. So these are the column strips along 6 meters. Now this total was 7. If you remember, 7.5. So column strip is 3. So half of 3, half of 3. So together this is 1.5, this is 1.5. So 3. Then our middle strip will be 7.5 minus 3, 4.5 meter. So that is what we'll write down here. Adopt column strip width of 3 meter and middle strip width is equal to 7.5 minus 3, 4.5 meters. I hope it is clear how to adopt, because we have to distribute the bending moments and the area of steel. We have to design the area of steel on these column strips. So this is how we have fixed up. Now we will go to the calculation of bending moment. So as I said you, before finding out the bending moment using IS clause, that is 31.4.2.2, we have found out how much, what is L1, what is L2, what is the clear spans, everything we have fixed up. What is the width of strips? So now we can calculate or we can determine or we can find the bending moments. Okay, so bending moment along longer span first, along longer span. So as I said you, when we are finding it along longer span, that span becomes L1, the other span becomes L2. Okay, So as per IS 456 clause 31.4.2.2, the design bending moment or the sum of positive and average negative bending moment is given as M0 is equal to WLN by 8. So this was over area. So that I can rewrite it as, because we are taking the this one along the long one span. So the other will come here. W2 into L2 into Ln. This is an area. I am converting the load which was over an area into the uh, load, point load, like this. Okay. So that multiplied by ln1. Okay. So because we are finding it at along longer span means L1 in this case, that is 7.5 meter. Okay. So by 8. So let us calculate how much is the bending moment. Total load, we found it as 17.8 2 kilonewton per meter square. So that I am multiplying the area so that it becomes kilonewton. Okay. So your L2 is 6 meters. You can see your L1 is 7.5 meters. L2 is 6 meters. Okay. Similarly, the clear spans L1, Ln1 was, we have determined it already, 6.16 meter, and the clear span in the other direction is 4.66 meters. Okay. So substitute those values here. 6 into Ln1 square, because there are, it's like this, W L2 Ln square by 8. So this becomes 6 into ln1 is 6.16 whole square by 8. So what we are doing is we are converting this load which was over an area into a point load by multiplying with area. So this is the area of the panel when you are considering across span 1. Okay, into the span 1 clear length by 8. Fine. So after we do the calculations, we are getting the bending moment as, okay, the total bending moment. This is the sum of the positive and negative bending moment as 507.14 kilonewton meter. So this is the total bending moment on coming on the panel, interior panel of span 7.5 meters and 7.5 meters by 6 meters panel, which is interior. Now this has to be distributed. Okay, this has to be like, out of total bending moment, you have to take the share of negative bending moment and share of positive bending moment. Again, as per IS clause 31.4.3.2. You can see here. Negative design moment will be 0.65 times the total bending moment, and positive bending moment will be 0.35 times the 0.35 times the, you can see it here, 0.35 times the total bending moment. So let us distribute that. Total negative design bending moment, negative design bending moment, or the design moment, I can say. Okay, so we will represent it like this: mu total negative portion. Okay, so as per IS 456, it is 0.65 times of total bending moment. So that is coming as 0.65 into 507.14. So finally it is mu negative will be 300, approximately 330 kilonewton meter. So same way, positive bending moment. 0.35 times the total bending. Positive design moment. So directly I'm writing down the value. Okay. M U O positive is equal to 0.35 times 507.14. Okay. So that comes out to be 177.5 kilo. So this is the positive bending moment. Okay. So for this we have to design negative steel, and for the other we have to design the positive steel. So but this has to be distributed. This has to be distributed across strip as well as across the middle strip and the as discussed earlier, we have to distribute this moment. For negative bending moment is near the supports. Okay, we have to distribute it to the column strip and middle strip. How much bending moment will be taken up by the column strip and how much bending moment will be taken up by the middle strip as per the again IS 456 clauses. So once we distribute those things, then we can calculate the maximum bending moment thickness. Fine. So our next step will be the distribution of the bending moments. So that will be our step 7. Okay. Step 7. Distribution of bending moment. Or I can say distribution of moments, that is positive as well as negative. Both bending moments in column strip and middle strip. Then accordingly we will get the steels. So distribution of positive moments in column strip and middle strip, distribution of negative moment in column strip and middle strip. So again following the IS 456 clauses. Fine. So 31.5.5.3. The it has given the distribution of moment, that is negative moment in column strip shall be you can see 31.5.5.3. 31.5.5.3. Okay. Yes. Here. For each span, the column strip shall be designed to resist 60% of the total positive bending moment. Same way here, negative bending moment. Before positive bending moment, there is the about the negative bending moment here. 75% of the negative bending moment should be adjusted to the column strip. 75% of the negative bending moment will be taken up by the column strip. So negative bending moment in the column strip will be equal to 75% means 0.75 times of MUO negative. So that is 0.75 into 330, 75%. So we get the negative bending moment in column strip as it's negative. So you can show it with a negative sign, 247.5 kilonewton meter. So this is the first bending moment in the column strip. Let us, just for remembrance, we will write it like this. So same way, let us do the negative bending moment or the negative moment in middle strip, the remaining one. So you can calculate either way. You can just remove out of 330, if you remove 247, whatever you get it, that will be provided in the middle strip. So that way you can do, or because 75% is gone, the remaining will be the 25%. So that way also you can do. M middle strip will be equal to minus 0.25, 25% of 330. So that is, minus indicates negative bending moment, 82.5 kilonewton meter. Fine. So this is how you have calculated the bending moment in the negative bending moment in the middle strip. Okay. So similarly, I can write similarly. Same step we will repeat for positive bending moment, but the percentages will be different. 60%. So column strip 60%. So let us find out positive bending moment in column strip. So that is like this. Is, you can write it if you want it here, 6.5 times of MEO positive. So this is 0.65. The positive bending moment which we got was 177.5, 35% of the total bending moment. So this we are getting it. This is positive. So you can just show it as plus 106.5 kilonewton meter. So this is okay. So last is the middle strip, right? The remaining moment of 177 point positive moment in middle strip. So let us write down 60. Oh, this is 60%. Okay, not 65%. This is 60%. Okay, so answer is correct. Only in the flow I have written it as 65. So M middle will be 60 is gone, so 40%. So 0.4 times of 177.5. So M it will be, middle strip positive steel will be equal to 71 kilonewton meter. Fine. So this is how we have found out the bending moments in each strip. In each strip, middle strip as well as column strip, both negative and positive. So we got a set of 4 bending moments. Okay. So in this, about 1 to 4, these 1 to 4 are called as, these are the above 4 moments that has to be considered for the design. So it will be a concrete design as well as it will be a steel design. So concrete means thickness. Steel means area of steel. So for area of steel, we will be using all the 4 bending moments. For positive column strip, we will use this bending moment. We will find out the appropriate steel. For positive middle strip steel, we will use this bending moment, fourth bending moment. We will get the area of steel in the middle strip for the positive bending moment. Same way we will calculate 4 area of steel. But as far as thickness is considered, we have to take the highest. Once you find out all the four bending moments across the longest span in the column strip, negative bending moment in the column strip, negative bending moment in the middle strip, positive bending moment in the column strip, positive bending moment in the middle strip. So out of this, the maximum we have to find out. The maximum bending moment we could find is column, negative column bending moment. So for this bending moment, we have to get the thickness of the slab. We have to find out the thickness. So when you determine the thickness, the width of the column strip shall be taken as 3 meters because the maximum bending moment is coming in the column strip. So the width of column strip shall be taken. Okay. Now, so using the formula mu is equal to 0.36 FCK B XU max D minus 0.42 XU max, we will determine the thickness of the slab from bending moment consideration. So what is XU max? XU max is the limiting depth of the neutral axis. So from IS 456 for FE 415 grade, the limiting depth of neutral axis is 0.48 times the thickness of slab. So once we substitute for maximum bending moment, we are getting the thickness of the slab as 173 mm. 173 mm. So providing an effective cover of 27 mm so that we get it to overall thickness as a whole number. We got the overall thickness from bending moment consideration as 200 mm. But from stiffness consideration, the thickness was 265 mm. So we have to take whichever is bigger value, that will be taken as the thickness, because if you adopt the lesser thickness, the slab may fail due to deflection. So to avoid that, we will take the thickness of the slab from stiffness consideration if that has got the higher value. So once we decided the thickness, we calculated the thickness, we have to go to the next step, that is step 9. Step 9, we are going to find out the area of steel. As you know, we have column strip, and then middle strip. We have respective bending moment in the column strips, positive and negative. We'll get all the area of steel's respective bending moments. So whatever steel we are finding out now, it will be provided in the longer span. For example, if this is my longer span, so whatever area of steel I get in the column strip, I will provide it that steel, negative steel. Okay. So whatever area of steel I get in the column strip, I will provide it for negative bending moment. Same whatever area of steel I get in the middle strip, I will provide that in the middle strip. Same way positive steel. Okay. So we have got 4 bending moments. So we will find out 4 area of steel. So first is negative steel in column strip. In column strip. So the column bending strip negative bending moment was 247.5 into 10 to the power of 6. Using the standard formula 0.87 FYAST into D into 1 minus, there is a standard formula in the code. This one, using this formula, we will find out the area of steel corresponding to each bending moment in each strip. Okay. So first I have taken the negative steel, that is negative bending moment in column strip. So the area of steel required in the column strip to resist the negative bending moment of 247.5 into 10 to the power of 6. Okay, I got an area of steel as 3142 mm square. Substituting everything in the given standard formula, I got the area of steel as 3142 mm square. Now, this has to be converted into the bars. Okay, so we will select 12 mm diameter bars and we will calculate the spacing. Area of one bar divided by total area of steel, because the width of column strip is 3 meters. The width of column strip is 3 meters. We will multiply with 3 meters. We got this as 118 mm center to center. So this is what I was saying. This is the column steel to resist negative bending moment, that is 12 mm at 118 mm center to center. Same way here also. Then there is a negative steel in the middle strip. So what was the bending moment? The bending moment was in the middle strip was 82.5. So once again, using the same formula, 0.87 FY into 1 minus ASTD by BDFCK. So once we substitute, I got the area of steel required to resist the negative bending moment in the middle strip as 980 mm square. I have selected 10 mm bars at 150 mm. I have calculated it as 150 mm center to center. Okay. Similarly, we'll find out positive steel bending moment, positive area of steel. Okay. So using the same, because we know the bending moment, how much it is, the positive bending moment in the column strip, it was 76, oh, 1 minute, it was 106.5. Okay, 106.5 kilonewton meter. So this was the positive bending moment in column strip. So this is the area of steel. Using the same formula, we got this area of steel to resist this positive bending moment. Same way, for the middle strip, the area of steel required to resist the positive bending moment of it was of 71 into 10 to the power of 71 kilonewton meter. To resist this bending moment, we need an area of steel as 840 mm square. So this is how we get the steel in the column strip as well as in the middle strip both for positive and negative bending moment. So in the same way, we have to once again calculate the bending moment across the shorter span, and we have to repeat the same step like this. Okay. The next step, that is step 10, we have to determine the bending moment along the shorter span using the same formula. Mu, that is the sum of positive and negative bending moment, is equal to Wu. Now here, there it was L2 longer span mein. Now in shorter span we got L1 Ln2 square by 8. So we get a positive bending moment along shorter span as 362.78 kilonewton meter. Now this bending moment again has to be distributed negative 0.65, positive 0.35. So once we get the negative bending moment and positive bending moment, again we have to distribute it in the column strip as 75% and in the middle strip as 25% in case of negative bending moment. And in case of positive bending moment, 60% of the total positive bending moment will be taken up by the column strip, and 40% of the total positive bending moment will be taken up by the middle strip. So the same step 9 is again repeated. Step 9 was the calculations of the bending moment along the longer span, then distribution, then area of steel. So same step 9 has to be repeated in step 10 across the shorter span. That was across the longer span, and this is across the shorter span. So once you finish that steel, again 4 types of steel, that is area of steel in column strip and area of steel in middle strip to resist negative bending moment. Third steel, area of steel in column strip, area of steel in middle strip to resist the positive bending moment. Okay, so you get again a set of 4 steels across the shorter span. So after finishing that steel design, we have to check for shear. As you know, flat slab is subjected to punching shear. The other name of punching shear is two-way shear. Okay, as we have done it in slabs, in a design of footing, the critical section for two-way shear will occur. Critical section for two-way shear will occur at a distance d by 2 from the face of column head. Okay. Now this figure, if we draw it, it will be easy for us to find out the shear force. Okay. So this is the size of panel, that is 7.5 meters by 6 meters. So in this is the size of drop, 1.34 by 1.34. This is the drop. So when failure happens due to two-way shear, this will happen at a distance d by 2 from the column head. So this is a column head actually. 1.34 by 1.34 is the column head size, which we already determined it. Okay. So this is at a distance d by 2, that is 120 mm, d by 2 120 mm from the column head. So this will be the punch. So 0.12, 1.34, 0.12. So the total size of the punch will be 1.58 by 1.58. A punch means a hole. So when the slab fails due to punching shear stress, a hole of this size will be forming into the flat slab. So this is the hole or the punch. So to get the shear force, maximum shear force is obtained using the formula: maximum shear force is equal to WU, that is the total load over an area, multiplied by area of panel minus area of punch. Okay, so the load over an area was 17.82 kilonewton per meter square. Area of panel is 7.5 by 6 minus area of punch is 1.58 by 5. So we got the total shear force as 75.74 kilonewton. So due to this shear force, the punching shear stress tau Vu will be equal to Vu by B0D. What is this B0? This is the perimeter of the punch. Okay, so this is the shear force 757.4 multiplied by 1000 for newtons. Okay, B0 is the punch perimeter. So there are 1.5 meters this side, this side, this side, this side. So four sides, 1.5 meters. So this gives you the perimeter of the punch multiplied by the thickness of the slab. So we got the punching shear stress due to the shear force in the slab as 0.49 Newton per mm square. Now we should see what is the permissible two-way shear stress. So if you go to the clause of IS 456, two-way shear stress, okay, you can find permissible shear stress is given by Ks into tau C. Ks into tau C. So what is Ks? It is clearly given in the code. Ks is equal to 0.5 plus beta. And this shall not be more than 1. This shall not be more than 1. I repeat, 0.5 beta, and this shall not be more than 1. So what is beta? Beta is the size of column, the shorter side of ratio of the longer side of column by shorter side of column if it's a rectangular column. But our column, because it's a circular column and we have converted this into a square, equivalent square, so it becomes 1. So on substitution, Ks will be equal to 0.5 plus 1. So this is 1.5. But it shall not be more than 1. So therefore, we will take Ks as 1. We got the value of Ks. What about tau C? In the formula, there is tau C also. So again, if you refer IS 456, tau C is given as 0.25 root FCK. So it is 0.25 root 20. So this is coming as 1.11 Newton per mm square. So let us see how much the permissible stress is coming. K is tau C. Okay. Ks we got it as 1, tau c as 1.11. So the permissible shear stress will be 1.11 Newton per mm square. So permissible is 1.11 Newton per mm square. Okay. So what the punching stress we got? We got the punching stress as 0.49. So which is less than the permissible stress. So we are the slab which we have designed is safe in two-way shear. Okay. So this is more than 0.49. That is tau v. Okay. So safe in two-way shear. So this is the only check required here. So with this the design is completed. With this the design is completed. Okay. Bye everyone.